In the name of Allah, the most gracious, the most merciful, I am Engineer Hani Kamil, and with supporting with Engineer Rami Al-Shishtawi, he will introduce himself.
This is Rabi Al-Shishtawi, Senior Testing and Commissioning Engineer.
So today we are going to use the simulation softwares to simulate our system and expect the abnormal conditions, and then we will use this faults or this abnormal condition, and we will test the protection relay to check its behavior if this abnormal condition happen during operation. So our topics today, we will simulate 380 over 115 over 33 kV substation by MATLAB Simulink. We will apply we will apply the final setting on 33 kV feeder over current and earth fault protection relay. Already we built this protection relay also on MATLAB Simulink in our simulation. We'll generate series of faults on 33 kV feeder, which can be expected to happen in real operation. Then we will export the faults to Comtrade files. We will import these faults by OMICRON CMC156, so we can make re-injection again for protection relay testing. And today already we have ABB RED670 protection relay, so we will make fault re-injection over this relay to check its behavior if this abnormal condition happen in network. And again we will check also Alstom MICOM P443 protection relay to check also its behavior for this abnormal condition. So now we will go in first stage. We will build our network by simulation or MATLAB Simulink. So I considered now we have 4 substations: substation 1 and substation 2, 3, 4, 5. So for substation 1, it is 380 kV substation, which will feed my substation 2 by 380 kV. And we have 2 circuits now, overhead lines, transmitting the power from substation 1 to substation 2. So in substation 2, we have 2 transformers. This transformer 500 MVA 380 over 115 over 13.8. It is auto transformer to step the voltage down from 380 to 115 kV. And then we have also transformers, 100 MVA transformer. It will step the voltage from 115 to 33 kV. And then we have 33 kV feeders. It's going to another substation to feed industrial area. So by underground cable, 33 kV cable. Also we have capacitor banks. So we will simulate now one case of operation. These transformers will be in parallel condition, bus section is closed, capacitor bank is in surface to enhance the power factor. And we have 2 faults now, fault in the far end in substation 3 and fault in our substation 2. For loads, I started to add normal load, and also I added some rectifier circuits. It will generate some harmonics, so this will be a challenge for protection relay because I added now some harmonics, and this actually it will be in the live operation, in the real operation, because you know now on the industrial area always have rectifier circuits like variable frequency drive for motor control, so always generating harmonics. So we need to make some practical simulation. So now load 1 and load 1, load 2, load 3. I added some rectifier circuits to generate some harmonics. Now for the far end or substation 3 fault, I make a fault for 80 milliseconds, and this fault resistance of fault 40 ohm. So this fault expected to only stay for 80 milliseconds and then will be cleared by the substation 3 or the far end protection relay and breaker. And then this feeder will work for no load for a time, and then this fault, due to the first fault, already some stress happened on our system, so the fault will be regenerate or reinitiate again, but in our substation 1, substation 2, but it's higher with higher stress fault, means it will be for 1 second. Actually I disable the protection I disabled the trip circuits, so it will not trip the circuit breaker, because I need to record the fault for more time. So because as you know, we will take the fault to re-inject again and retest the protection relays. So also I make the fault resistance 2 ohms to generate higher fault. And of these faults are actually fault 1 and fault 2, it will be phase to ground fault. Now in my protection for transformer number 2, for substation number 2, for this feeder, I have overcurrent and earth fault relay, and we have some measurements here. We can check also voltage of each phase and neutral voltage displacement, voltage total harmonic distortion current for each phase and neutral, and total harmonic current distortion. Our protection relay here, actually this block I built it because there is no block in MATLAB Simulink, so also you can build the same block, and I make some graphical user interface so it will become easy to change the setting. So first we will enter CT and VT data. We'll enter the CT and VT ratio and system frequency, as you can see. Then we'll go to function and parameter setting. Now we enabled only phase over current, time delay, and instantaneous, earth fault over current, earth fault over current, time delay, and instantaneous. Negative sequence and breaker fail, we disabled it because this is the final setting actually in breaker in real substation. Our substation case, it's already disabled, so I disabled also in simulation. So now first stage or time delay over current, this is the setting, current setting 1, and standard inverse IEC standard inverse curve, and time multiplier setting is 0.25 and non-directional. Stage 2 or instantaneous, current setting is 3 and time delay is almost 0. Here I put sampling time is already 0.1 0.1 milliseconds, or almost zero, and also non-directional. Now we'll go to earth fault, time delay earth fault. What will have this setting 0.2 and IEC standard inverse, and also 0.25 time multiplier setting, and non-directional also. And in instantaneous stage it will be current threshold is 1.5 and same time delay is 0, or with the sampling factor, sampling time, and also non-directional. Now our protection relay ready and our system is ready. Here we can, by this scope, we can check the operation, which start and which trip. Now we'll make run. Now our system running. We can find now our feeder now still our breaker is not closed, so our system now there's no voltage and no current. Now our breaker is closed in substation 2. It will now feeding the underground cable and load in substation 3. Actually, when the breaker on, it starts to feed load directly, and also it will have some inrush current due to charging and inrush current of load and loading current. We can see now the total harmonic distortion in voltage and volt and current. Now as we can see now already first fault now happen and cleared. It's happen in 80 milliseconds. We can see in the scope. And now again, so already the first fault happened in substation 3 and cleared. Now the system feeding only the charging current of the cable, so the small current. Now the fault will transfer and reinitiate on our substation 2. It is now higher fault. As you can see, it will stay for 1 second, and after 1 second it's cleared. As we said, I already isolated the trip circuit, so and I kept only the fault for 1 second. So now we will check the disturbance record. As we can see, this is the state or the time of closing the breaker and feeding the load. It will have some inrush current plus the loading current. So it's in yellow phase. As you can see, it's already more than the setting. So we have overcurrent start, but there is no trip because the time it was less than the time delay overcurrent. Then we make fault in substation 3, and it's only for 80 milliseconds. It's cleared by substation 3, and so it starts the protection here. It is earth fault started and phase overcurrent started, and because this stage is time delay overcurrent and earth fault, so it started no trip, only the trip and cleared by substation 3 for in substation. Again we reinitiate another fault, but we see it is a higher fault, higher current. It's in instantaneous stage, so just the current with these values start happen, and on the same time the trip also happen. It is earth fault and overcurrent in instantaneous. You can see now the curves. as you can see, I will just here in the curve just deactivate the earth fault trap, so we can see to check to check is overcurrent signal already or trip signal already available, but again we'll highlight it so we can see that it is overcurrent and earth fault already instantaneous trip happened. And same in starting circuit or starting condition. Now we are second stage, we are going to export this fault to Comtrade files. So I built a code. This code I write in M file. Just I will click run. It will take this voltage data and analog data and current data for the fault and in substation 1, and it will generate a Comtrade file. So we can take this Comtrade file and we retest again our protection relay to check its behavior if this condition happen in operation. Just I will click run and already order executed. So we can go to same path in our software. We'll find the fault already exported, as we can see. Again, so the path now is available. Just it is my fault is named fault 1. It's already available. So I will take this fault. We can see here I open by Sigre software, so we can see the breaker closing time is voltage signal and current signal. So this breaker closing time already phase yellow phase already its current is higher than the setting, so it will start the overcurrent, time delay overcurrent and earth fault. But because it's small time, so it will not trip. Then again the far end fault, and already it was for 80 milliseconds and only cleared by the far end protection system, because its time it is cleared before our system reaches to the trip time. And also now this fault current in our system substation 2, which already happened direct in substation, and it was higher current, so it stripped directly. But as I said, just make it for 1 second so we can test our protection relay to check complete behavior, whatever the time delay we got. It's already 0 seconds, but nothing is 0 seconds. We need to check its behavior, how much time it will take. So I make it for complete 1 second. So now this is a fault. I will handle to engineer Rami Al-Shishtawi. He will start now. So I will let him to start his part.
Today we are going to re-inject a MATLAB simulated fault on a 33 kV feeder using a disturbance Comtrade file extracted from MATLAB Simulink. As a testing equipment, we are using CMC156, one of OMICRON products, and Test Universe 3.20 as operating software. Now let's check how a relay will behave based on injected fault, and for the study we have two relays, RED670, this is a ABB product, and MICOM P443, this is a Alstom product. Okay, now this is the Comtrade file that was extracted from the MATLAB Simulink that we need to use to re-inject the fault again using the CMC156. We will use a operating software as the Test Universe 3.20. We will use the transplay feature. Then we have to import the Comtrade file. Okay, we'll choose add to list. We'll import this file. We have to make sure this is the one, yes. Fault 1. we will edit the ratio to be 1 because the Comtrade file values were created by the secondary values, and this will be the injection values. Now the software is converting the Comtrade file to injecting values. Okay, we'll select play files. The total duration of the event is 5 seconds. Now the test equipment CMC156 will inject the full event 5 seconds to the relay. We'll start with the ABB relay RED670, and the photo of the LED and the relay behavior will be attached. Now we have to extract the disturbance to check how the relay will behave using the PCM600 2.8. So obviously 3 events happened. We will extract, we will export, yes, we'll read the recording from the relay to check one by one and to check what happened. By analysis of this disturbance, we will know how the relay will behave. We're just exporting. I named the folder Hani for Mr. Hani Kamil, who created the Comtrade file. We'll just name it 1, 2, 3 just for the order of the events. So it's not necessary to do that. Okay, 2. We already named that once. Okay. Okay, whatever. We'll start with the first one. We can see this is the closing. This is the first event, is the closing point of time. At that time, we have some around with the secondary value around more than like around 0.9 ampere. Okay. Only phase B, the second phase started. Time over current start, 51 over current start, 51 phase B start. So this is what happened, only the start during the closing because of the charging, line charging current and the rush current. So no trip, only starting for the function. The second event is the fault at the far end of the feeder that was already cleared by the breaker at the load, not at the feeder breaker, but the far end breaker. You can see here the current values. It's a little bit high. It will make it's around 0.8. You can see how much. Okay, 870 milliamperes. It will cause the ground time of a current to start. Okay, yes, time of a current, time earth fault. 51N earth fault start. Okay, but without any tripping because the fault is already cleared from the far end of the line. Okay, for the third one, the third event, this is the fault event. We can see the current. The current here is around 10 amp. Yes, 9.86 amps. And the instantaneous overcurrent setting here is 3 amps in this relay. So the instantaneous function will operate. Okay. We can check that through the timeline of the disturbance record. General trip. Okay. Acute trip on phase A. Okay, phase 1. Time earth fault started. Okay. After the definite time, the time earth fault tripped. Okay. Time overcurrent tripped also after the definite time. 51 overcurrent start. 51 phase A start. 50 instantaneous overcurrent trip with no time delay. Instantaneous, it's a 0 time delay. And the 94, the lookout relay operated. Okay. So this is the fault. This is the fault disturbance record. Okay. Now we have to inject the second relay. Inject the Comtrade file using the test universe again, but to the second relay which we have is MICOM P443, one of the Alstom products. We'll use again the transplay feature in test universe. We will use the same Comtrade file so we can compare between the two relays. We'll add yes, we'll use fault 1. This is the one we used. We have to make sure of the ratio. Again, yes. It's converting. We'll play. So we can check the relay behavior. Okay, it's injecting now. Okay, it's already injected. We'll go now to check the disturbance records from the relay. We'll extract it. Oops, we have to connect the connection first. The serial connection. We are using the RS232 serial connection. This is the list of the disturbance that occurred. So this is the last 3 events that happened and they triggered the disturbance recorder in the relay. We will extract it one by one. Just will make pause for a little time because it's taking some time. The extraction maybe will take you a minute or two. Okay, we extracted. We have now to export from the software. It's simple. We'll just copy and paste. Just Control-C, Control-V. Yes, we'll copy to the same destination with for our beloved Mr. Hani folder. Okay, just for the order, we'll name it 456. You can say just for fun. Okay, the last one. We'll name it 6. Now let's check one by one. Okay, this is the closing. This is the closing time, the currents. Let's check what happened in the recorder. The same, just started. Okay, the time earth fault started only without any tripping, because this is the charging current and the inrush current. So no trip happened at the closing. The second event, it should be the fault that happened at the far end. It should start also the function without any tripping. We can see the current values here. Nearly same as the ABB relay. We can see also is time over current started and time earth fault started also without any tripping, because the fault was cleared from the far end, from the load breaker. And the last one, this is the fault in front of the feeder. We can see here the fault current is high enough to operate the instantaneous overcurrent function. We can see time overcurrent function start, instantaneous start, time earth fault start, instantaneous earth fault start, all started. Time overcurrent and time earth fault tripped after time delays similar to the ABB relay, and also instantaneous earth fault and instantaneous overcurrent tripped also. So the behavior same what happened with ABB relay. And this is the simulation and re-injection of a simulated fault extracted from MATLAB. Thank you so much. Thank you to Mr. Hani Kamel.
Thank you, Engineer Rami, for your support, and thank you for all. This is our contact. Anyone have idea or have clarification or something not clear, he can contact me and contact Engineer Rami. And thank you for your watching, and see you in next video.